horizontal asymptote rational functions. You're listening to a lesson in differential calculus. This one is designed for non-math majors. Given two polynomial functions p of x and q of x, the rational function f of x takes this form. It is a ratio of two polynomial functions, where q of x is not equal to 0. So the domain of our function is the set of real numbers minus the set of x's where the denominator is equal to 0. So last time, I showed to you a few graphs of rational functions. I spoke about the vertical asymptotes. I spoke about, in passing, about the horizontal asymptote. And I think that I was not able to speak sufficiently about horizontal asymptotes. Asymptotes are not always horizontal, okay? We have vertical asymptotes. We already spoke about them. But asymptotes can also be slanted, okay? We call them oblique asymptotes. And later I will show you what are the conditions that give way to oblique asymptotes. So given a rational function f of x, the line y is equal to b is the horizontal asymptote if and only if y approaches b when x approaches infinity or when x approaches negative infinity. So this x and y here, these are the coordinates of the points of your graph, okay? And so as x approaches infinity, there is a corresponding values for y. And whenever this is true, okay? Whenever this is true, then the line y is equal to b is going to be your horizontal asymptote. In this example, when x approaches infinity, what that means is when x takes on values that grows positively to infinity, the value of your function or the y-coordinate of the points of the graphs of your function approaches the horizontal axis. And the equation of your horizontal axis is y is equal to 0. This one has a different horizontal asymptote. When x approaches infinity, your y, the values of your y approaches this line, y is equal to 1. And the same here, When x approaches negative infinity, okay, when the magnitude of your x increases, but it's negative, the value of your function, okay, the value of y also approaches the line y is equal to 1. So in this case, this is your horizontal asymptote. Now we have three cases. So let's say f of x is your rational function, okay? And m here is the degree of p of x. It's the degree of your polynomial in the numerator. And n here is the degree of q of x. Now this is the first case. If n is greater than m, okay, so if the degree of your denominator, the function in your denominator is greater than the degree of your function in the numerator, the horizontal asymptote is the line y is equal to 0. For example, so this one is a rational function in which the numerator is a constant function. It is a polynomial function of degree 0. The denominator is a quadratic function. So n here is greater than m. And so in which case, the horizontal asymptote of your function is this line, okay? This line. And that is the line defined by y is equal to 0, okay? Here, the function in your numerator, the polynomial function in the numerator is a degree 1 function, but the function in your denominator is a degree 2 function. So n is greater than m, and in this case, your horizontal asymptote is the line y is equal to 0. Okay, so let us show why this is so. Why it came to be that way by showing to you an example. So let's say our function is this: x plus 2 divided by x squared minus 1. The degree of your polynomial function in the numerator is 1. Here, the degree is 2. So n is greater than m. Okay, we were told that the horizontal asymptote of this function is the line y is equal to 0. Okay, so why did it came to be that way? So look at this. X plus 2 over x squared minus 1 is equivalent to this. Now, why so? Why so? Why is that equivalent to this? Because this one is just equal to 1. And any non-zero real number multiplied to 1 is equal to itself. So these two functions are equivalent. Now, you might be wondering, and you are asking me, why did I multiply this by this? Okay? I asked myself that. In my mind, I was asking my teacher that when I was a student, when I first saw this. What will come out from the solution is the explanation, okay? You will only know why this must be done when the solution is done. Okay, so what I will do now is I will multiply 1 over x squared to the terms of your polynomial function in the numerator, and this same with this. I will multiply it to the terms in your denominator, and this is the result. X over 1 over x squared is 1 over x. 2 times 1 over x squared is 2 over x squared. And then x squared times 1 over x squared is 1. And then 1 times 1 over x squared is just 1 over x squared. Now, what happens? What happens with the y coordinates of your function when x approaches infinity or negative infinity? What happens with the value of y? Well, when x approaches infinity or negative infinity, this term approaches 0. Okay? So imagine 1 divided by 1 billion. That is almost like 0. The same with this. So your numerator approaches 0. The value of your numerator approaches 0 when x approaches infinity or negative infinity. Now let us look at the denominator. So this one is constant. It is not affected by your x's. But this one, when x approaches infinity or negative infinity, this term approaches 0. So this becomes this, okay? 0 over 1 minus 0, and that is equal to 0. Okay? So conclusion, y approaches 0 when x approaches negative infinity or positive infinity. Now, this time we will pay attention to the coefficients of the leading term. Leading term of the numerator and leading term of the denominator. So if n is equal to m, the horizontal asymptote is the line y is equal to a sub m divided by b sub n. Or the horizontal asymptote is the coefficient or the numerical coefficient of your leading term in the numerator divided by the numerical coefficient of your leading term in the denominator. So for example, this statement is telling you what ought to be the horizontal asymptote of this rational function. The numerator is a degree 2 polynomial function. The denominator is a degree 2, n is equal to m. So we will pay attention to the numerical coefficients of your leading term. Okay, here a sub m is equal to negative 2, b sub n is equal to 1. We were told, okay, so we are told that the horizontal asymptote of this function ought to be negative 2 divided by 1. And why is that so? Why is that so? Okay, look at this. So this and this are equivalent functions. Why? Because this is just equal to 1. Okay? Any non-zero real number multiplied by 1 is equal to itself. Now look at what happens here. I will apply the distributive property of multiplication over addition. You will multiply 1 over x squared to each of the terms in your numerator, and you will do the same with the denominator. And this is the result. Now, let us see what happens to the value of your function. Okay? The value of your function is the y-coordinate of your points. What happens? What happens with the value of your function when x here approaches infinity? Let us see. So again, when x approaches infinity or negative infinity, this one goes to 0. This one goes to 0, but this one is not affected. It's constant. It's negative 2. Now when we go to the denominator, this one is also constant. It stays as 1. And then this one, when x approaches infinity or negative infinity, this one approaches 0. And so this is the result. This is what happens with the y coordinates when x approaches infinity. It approaches this value, and that is negative 2. Okay? So this is your horizontal asymptote. So this is the graph of that function. Okay? As x approaches infinity, the value of your function approaches negative 2. And it's the same here. So when x here goes to negative infinity, the value of your function approaches negative 2. Now, what happens when m is greater than n by 1? In which case m is equal to n plus 1. When these are the degrees of your numerator and the denominator, the asymptote that will appear is what we call the oblique asymptote. So it is not horizontal, it is not vertical, it is slanted. And you will obtain the equation of that oblique asymptote when you divide the numerator by the denominator, and then you will pay attention to the quotient. The quotient will define the equation of your oblique asymptote. So for example, this one, f of x is equal to x squared minus 2x plus 1 all over x plus 1. So here, m is equal to 2 and n is equal to 1. Okay, so let us derive the equation of your oblique asymptote. So what you do is you do the division. Okay, you perform long division, and this is what you will get. Okay, this is the quotient plus the remainder, and this line. Okay, the line y is equal to x minus 3 defines the oblique asymptote of this function. Okay, so when x approaches infinity or when x approaches negative infinity, the value of your function will approach this line, okay? Y is equal to x minus 3. This is the summary. Given a rational function f of x is equal to p of x over q of x, we are assuming that it is already in reduced form, okay? M is the degree of your function in the numerator, n is the degree of your function in the denominator. So these are polynomial functions, okay? And a sub m and b sub n are the numerical coefficients of the leading terms of your numerator and denominator. So we have three conditions. If n is greater than m, the horizontal asymptote is the line y is equal to 0. That is the horizontal axis. Okay? The second condition, when n is equal to m, when their degrees are the same, the horizontal asymptote is the line y is equal to a sub m divided by b sub m. So the degrees of our numerator and denominators are the same. Conclusion, the horizontal asymptote is going to be the numerical coefficient of the leading term in the numerator divided by, okay, you have one here, the numerical coefficient of your leading term in the denominator. This is the horizontal asymptote. It's negative 2 over 1. When m is greater than n by 1, or when m is equal to n plus 1, the graph has an oblique asymptote. It is a slanted line. You can obtain the equation of that line by dividing the numerator by the denominator. The quotient is the equation that will define your oblique asymptote. Okay? So here, m, the degree of your numerator is 2. And the degree of your denominator is 1. Okay, so this one applies. The oblique asymptote is given by y is equal to x minus 3. And you can get that equation by dividing the numerator by the denominator. So the quotient is what will define your oblique asymptote.